Okay, let's dive right into this explainer and decode exactly what Cambridge examiners are looking for in your Physics 0625 thermal physics answers. Welcome to the ultimate masterclass on setting your field, reading the examiner like a pro bowler, and scoring your maximum runs, which in our case means maximum marks. Think about it like a game of strategy. Now, look at our two hypothetical students. First, we've got Alex. Alex is undeniably brilliant, but Alex overloads the page with raw physics facts about particles, completely ignoring the actual analysis the question is asking for. It's just a brain dump. Then we have Sam. Sam rushes the paper, completely misses the crucial command words, and loses easy points. Their flawed answers, usually covered in the examiner's dreaded red pen marks, are exactly what we're going to transform into solid green check marks today. We're focusing heavily on syllabus code 0625, specifically topic 027. This covers melting, boiling, condensation, and solidification. Honestly, if you've ever lost marks when explaining energy input without a temperature change, and let's be real, who hasn't, this analysis is going to be your absolute lifesaver. Did you know that concepts like melting, boiling, condensation, and solidification account for approximately 15% of your total examination marks? Yeah, 15%. That is a massive chunk of your final grade sitting in just one subtopic. When we talk about these thermal processes, examiners are constantly, relentlessly testing your understanding of the microscopic kinetic model. They want to see if you truly grasp what happens to water at standard atmospheric pressure when it hits exactly 100 degrees Celsius. Like, why does the temperature just stop rising even though you're still pumping thermal energy into the system? This 15% margin is exactly where the difference between a B grade and an A star is decided. It's literally the make or break zone. Students like Sam lose out here because they offer these vague, fuzzy descriptions instead of precise particle-level physics. Well, we're going to fix that today so you can capture every single percentage point available in this crucial topic.
We are going to break down this topic systematically. First, we'll cover core principles. Second, the procedural framework. Third, examiner warnings. And finally, top score analysis. Let's get moving.
All right, starting with Part 1, Core Principles. Let's look at the theoretical architecture of thermal physics and how it targets your knowledge, application, and analysis domains.
You see, Cambridge isn't just testing if you memorize that boiling happens at a specific temperature. Anyone can memorize that. They are testing how you apply that knowledge to totally novel situations and how you analyze the data they give you. To conquer this, you need a system. You need the PEL framework for physics: point, evidence, explanation, and link. So, when you're asked to describe melting in terms of particles, your point is the state change itself. Your explanation must detail how the thermal energy input is being used to overcome intermolecular forces, breaking the bonds between particles rather than increasing their kinetic energy. That right there satisfies the core principles of the mark scheme. What's really interesting is the method mark strategy. Examiners prioritize your evidence-based reasoning and systematic analysis, not just that final numerical answer at the bottom of the page. Say you're calculating the specific latent heat of vaporization, right? And you make a tiny, silly calculator error at the very end. You don't lose all 4 marks, provided your process is clearly laid out. You literally have to write down the formula, show the substitution, and explicitly state your units. Examiners actively search your working for opportunities to award you marks, so give them something to find. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
So jumping back in, here's a brilliant insight pulled directly from the principal examiner reports. Candidates who connect thermal physics to other syllabus areas achieve significantly higher scores. It's like a giant puzzle, and you get rewarded for showing how the pieces fit together. You really shouldn't view melting and boiling in isolation. When you discuss condensation, a gas turning into a liquid, the absolute elite students link this back to the kinetic theory of matter. They explain that as the gas cools, particles lose kinetic energy. They move slower. And as they get closer together, those intermolecular forces of attraction become strong enough to hold them in a liquid structure. It's a complete narrative. Furthermore, connecting the boiling temperature of water to standard atmospheric pressure bridges thermal physics with your pressure topic. If atmospheric pressure drops, what happens? The boiling point drops. Showing the examiner that you understand this interconnected web of physics is basically guaranteed to elevate your grade profile.
Let's move to Part 2, the procedural framework. Let's see how this builds into the exact methodology you need to use in the exam.
We're shifting from theory into application now, giving you what we call the physics success blueprint. This procedural framework completely takes the guesswork out of your exam. No more staring at a blank page, sweating, wondering how to start a heavy 5-mark explanation question. By standardizing your approach, you can conserve mental energy and ensure that every single sentence you write is hunting for a mark. Imagine a question asking why the temperature of a melting ice cube stays at 0 degrees Celsius despite heat being actively applied. Step 1. Identify key elements. Well, the command word is explained in the context as melting. Step 2. Apply principles. We need kinetic theory and latent heat. Step 3. Execute analysis using that Peel framework we talked about. The thermal energy being supplied is not increasing the kinetic energy of the molecules, hence the temperature remains constant. Instead, the energy is doing work against the intermolecular forces, overcoming them to change the solid structure into a liquid. Step 4. Verify. Did I mention particles? Yes. Did I explain the constant temperature? Yes. Step 5. Present format. Ensure it's logically sequenced so the examiner can actually follow your train of thought.
Presentation of information follows strict conventions. You must use proper headings, correct terminology, and clear annotation. This is how we transform Alex and Sam's red pen marks into green check marks. Never, ever just write bonds break. Write intermolecular forces are overcome. Never write particles get hotter. Right? Average kinetic energy increases. Precision is absolutely everything here. You need to keep your terminology sharp and your presentation flawless. When the examiner sees a beautifully laid out, clearly annotated answer, they are psychologically primed to award you higher marks. They're thinking, okay, this student knows their stuff. By the way, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Moving on to Section 3, Examiner Warnings. Let's look at the top traps students fall into directly from the examiner's desks.
Think about it. The examiners read tens of thousands of papers every single year, and they see the exact same mistakes repeated over and over and over again. It doesn't matter how well you know the underlying physics if you fall into these specific contextual traps. Let's do a quick challenge. Imagine a cooling curve graph. Those horizontal, flat plateaus represent condensation and solidification, where energy is being lost to the surroundings, but the temperature isn't dropping. The absolute classic mistake when analyzing this is providing memorized generic answers. Take a look at this flawed sample physics paragraph. Evaporation happens when particles gain energy and leave the liquid. This cools the liquid down. If you read it carefully, can you spot the flaw? It's entirely generic. If the exam question asks about a worker sweating on a hot day, you get 0 marks for that generic textbook definition. A context-specific, top-scoring answer would read, thermal energy from the worker's body provides the necessary latent heat to the sweat. The most energetic water molecules in the sweat overcome intermolecular forces and escape as a gas. Because the particles with the highest kinetic energy leave, the average kinetic energy of the remaining sweat decreases, effectively cooling the worker's skin. Do you see the difference there? Context is king. You have to link it back to the scenario.
Let's unpack these top 3 mistakes a little further. Examiners frequently report that students confuse cause and effect when explaining condensation and solidification in terms of particles. You have to be strictly precise with your causal relationships. For example, students often write, condensation happens because water droplets form. No, that's confusing the effect with the cause. The actual cause is a decrease in thermal energy, leading to a decrease in the particle's kinetic energy. As a result, the particles move slower, the intermolecular forces draw them closer together, and then the gas condenses into a liquid droplet. So as a quick speed writing exercise in your head, think about drafting one perfect paragraph right now explaining solidification. Remember, don't confuse cause and effect, check your terminology, and ensure you specify that during solidification, particles lock into a fixed regular lattice structure as bonds form, releasing latent heat without any change in temperature.
Under exam pressure, your mind can go blank. To make sure you never mix up these phase changes when the clock is ticking, we need to lock them into your brain. Here's a memory hack challenge for you. Try creating a mnemonic using the first letters of these key terms: melting, boiling, evaporation, condensation, solidification. M-B-E-C-S. Maybe something like, many brilliant engineers can solidify? Or whatever works for you, honestly. A really strong mnemonic ensures you instantly recall the directional flow of thermal energy, whether it's actively going into the system to break bonds or leaving the system as bonds form. Building these little cognitive shortcuts is absolutely crucial, ensuring you have total, instant recall when you sit down in that exam hall.
Finally, let's step into Section 4, Top Score Analysis. We are going to dissect the critical analysis techniques that separate the good physics candidates from the elite top-scoring candidates.
The top 5% of candidates in the world don't just know the facts, they know how to deeply evaluate physical systems. We've talked about the complete physics answering system. Rule 1, command word decoding. Rule 2, meticulous PEL framework application. And Rule 3, a time management matrix that ensures you don't spend 20 minutes on a 3-mark question. But to reach the absolute highest grade boundaries, you must demonstrate evaluative thinking. You evaluate the quality of evidence by identifying limitations and understanding how your assumptions affect your final conclusions. For instance, imagine a question asking you to calculate the energy required to boil water at standard atmospheric pressure using an electric heater. The basic student just blindly plugs numbers into the equation and moves on. The elite student, however, recognizes the hidden assumptions. They will actually write down that the calculation assumes 100% efficiency of the heater and assumes zero thermal energy is lost to the surrounding environment. In reality, energy is lost to the surroundings, meaning the actual energy input required will be higher than the calculated theoretical value. Pointing out these physical realities, limitations, and alternative interpretations is exactly how you impress the principal examiner and secure those highly coveted top band marks. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
So I want to leave you with this vital question. What hidden assumptions are costing you marks in your past paper answers? Are you assuming the examiner knows what you mean when you write a generic sentence about particles? Never assume. Explicitly state the particle behavior, the energy transfers, and the exact physical context of the question. Until you address your hidden assumptions, you are quite literally leaving marks on the table. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.